Hi, welcome to Sunil Maths tutorial, Functional Analysis class number 55. In this video, we learn a definition and a theorem. Let us see the definition, one of the very important definition, normal operator. So, let us take capital H be a Hilbert space. Let capital H be a Hilbert space and capital T is an operator, capital T is an operator defined on H, then this operator T is called normal operator. This T is called normal operator if it commutes with adjoint. If it commutes with its adjoint. Remember that commutes means commutative property AB is equals to BA. Adjoint, the adjoint of T is T star. So what it means here, it commutes with its adjoint means, T star is equals to T star T, where T star is the adjoint of T. So we conclude that, therefore we conclude that capital T is normal, implies and implied by T star is equals to T star T. Very important definition, remember that. Capital H be a Hilbert space, capital T is an operator defined on H, then T is called normal operator if it is commutes with its adjoint, that is T star is equal to T star T. It means capital T is normal operator implies and implied by T star is equals to T star T. So here now we know that self-adjoint operator definition. An operator T is called self-adjoint. T is self-adjoint implies and implied by T star is equals to T. If T star is equals to T, then obviously T star T is equals to T star. T star implies and implied by this is nothing but normal. So remember that it means every self-adjoint operator is normal. Every self-adjoint operator is normal. So this is the definition of normal operator and the relation between self-adjoint and normal. Now we prove the theorem. Let us see the statement. The set of all normal operators on a Hilbert space capital H is a closed subspace of script B of H. It is nothing but the set of all operators defined over H, which contains the set of all self-adjoint operators, and it is closed under scalar multiplication. So right, we prove this theorem. Let capital H be a Hilbert space and script B of H be the set of all operators defined on capital H. Now we define a new set. Let capital M be the set of all normal operators defined on capital H. Capital M be the set of all normal operators defined on H. Obviously, script B of H is set of all operators. So normal operators also lies in this all. So then this M is subset to B of H. But we have to show that, we have to prove that this M is closed subspace. This M is closed subspace of B of H. This M is closed subspace of B of H. To prove that M is closed subspace of B of H, let us define a limit point. Let capital T be the limit point of M. Let capital T be the limit point of capital M. To prove that M is closed, it is equivalent to prove that this T belongs to capital M. T belongs to M means T is normal. You have to show that T is normal. So, I repeat again. Capital M is the set of all normal operators defined on H. Then obviously M is subset to H. Our aim is to show that M is closed subspace of B of H. So to prove that M is closed, define a limit point. Capital T be the limit point of capital M. Since T is the limit point of capital M, then obviously there exists a sequence Tn of distinct points of capital M such that this Tn converges to T. As n tends to infinity. So because T is a limit point of M. T is a limit point. By the definition of limit point, there exists a sequence Tn of distinct points of M such that Tn tends to T as n tends to infinity. Now, we consider that Tn belongs to M. It means for all n, it means Tn is normal operator. Tn is normal means Tn star Tn is equals to Tn T star, and every normal operator is also self-adjoint. So Tn is self-adjoint. It means Tn star is equals to Tn. Now, therefore, we conclude that Tn star minus T star is equals to Tn minus T whole star norm of which is equals to norm Tn minus T, which tends to 0 as n tends to infinity. Therefore, this shows us Tn star tends to T star as n tends to infinity. Now consider one norm Tn. Now consider norm T star minus T star T, which can be written as norm. Let us add and subtract some terms. T star minus Tn star plus Tn star minus T star T. Please observe clearly. I add and subtract these two terms. Now it can be written like this, which is equals to norm T star minus Tn star plus Tn star minus T star T norm. Let us split the norm. If you split the norm, this equality becomes less than or equals to norm T star minus Tn star plus norm Tn star minus T star T. So which is again less than or equals to, it can be written as T star. You see here, Tn star Tn is equals to Tn T star, At the same time Tn star is equals to Tn, and now Tn star minus T star tends to 0. It means Tn star tends to Tn. So this condition implies as here this condition implies as just a minute. Here which is less than or equals to T star minus Tn star plus norm Tn star minus T star norm minus T star T. Also here again the same thing you have. Whenever this is tends to 0 means from this inequality Tn tends to T. Tn tends to T. By applying that result here, T star minus T star plus norm T star minus T star T, which is clearly less than or equals to 0. But what is in the left side? We have norm T star minus T star minus T star T is less than or equals to 0. But always norm T star minus T star T is greater than or equals to 0. This condition implies as this norm is equivalent to 0. Norm T star minus T star T is equals to 0, which implies as T star minus T star T is equals to 0, which implies as T star is equals to T star T. This is nothing but the condition of normal operator. Capital T is normal operator. If capital T is normal operator, then T belongs to capital M. What is T? T is limit point. What is T? T is limit point of capital M and lies in capital M. This shows as M is closed. Therefore, capital M is closed subspace. Of B of H. Now it is remaining to prove that it is closed under scalar multiplication. Before going to prove that, I can explain this derivation part one more time. Please observe carefully. Here, Tn is a sequence of terms in capital M. It means Tn belongs to capital M. It means Tn is normal. It means Tn is normal means Tn star Tn is equals to Tn star. And also every normal operator is self-adjoint. So you can simply write Tn star is equals to Tn. Now from this you can calculate like this. Norm Tn star minus T star is equals to norm Tn minus T. And already we said that Tn is a sequence converges to T, which is equals to norm T minus T, which is equals to 0. It means Tn star converges to T star as n tends to infinity. Already we have Tn tends to T as n tends to infinity. Now this put this derivation part in your mind. Now we calculate one simple norm T star minus T star T, which is equals to, I add and subtract like this, norm T star minus Tn star, I add the same term, Tn star minus T star T. Split the norm. If you split the norm, obviously this equality becomes less than or equals to norm T star minus Tn star plus norm Tn star minus T star. So already we said that Tn star tends to T star, Tn tends to T as n tends to infinity. By using these two results, this inequality becomes less than or equals to norm T star, Tn tends to T, Tn star tends to T star, plus again also same T star minus T star, which is less than or equals to 0 plus 0 equals to 0. So you simply get norm T star minus T star T is less than or equals to 0. But norm is always positive. Norm is always positive. So norm T star minus T star T is greater than or equals to 0. Combining we get T star minus T star T is equals to 0, which implies T star is equals to T star T, which implies T is normal. T is normal. If T is normal, then T belongs to capital M. It means limit point of M lies in M. Limit point of M lies in capital M. Therefore, M is closed subspace of B of H. Next, we have to show that it is closed with respect to scalar multiplication. So let us take alpha is a scalar. Alpha is a scalar and T belongs to capital M. T belongs to capital M. Now alpha T whole star is equals to alpha bar into T star. Alpha bar into T star. Now consider alpha T into alpha T whole star is equals to alpha T into alpha bar T star, which is equals to alpha into alpha bar T star. Alpha into alpha bar T star. In a similar manner, you can write alpha T whole star into alpha T is equals to alpha bar T star into alpha T. It can be written as alpha bar alpha into T star T. Already we said that T belongs to M. T is a normal operator. So T star is equals to T star T. That can be written as mod alpha square into T star T. Here also it can be written as mod alpha square into T star T. So now you observe this derivation part in both the places. Here alpha T whole star is equals to mod alpha square T star T. Alpha T whole star into alpha T is equals to mod alpha square T star T. It means you can conclude like this: alpha T into alpha T whole star is equals to alpha T whole star into alpha T. This condition shows as alpha T is normal. Alpha T is normal. If alpha T is normal, then alpha T belongs to capital M. Therefore, for any scalar alpha and T belongs to capital M, implies as alpha T belongs to capital M. Therefore, M is closed under scalar multiplication. This completes the proof of our theorem. Hence proved. We wish to prove the same thing. Keep learning. Wish you all the best. In the next video, we learn one more theorem depends upon the normal operator.